So welcome back to topic 2.1. This is part 2, the definition of a tangent line with a slope m. So if f is defined in an open interval containing c, and if the limits exist, then the line passing through the point c, comma f of c, with slope m is tangent to the line to the graph of f at point c, comma f of c. So pretty much that's what you guys see right there is what our equation, right, our definition at a point for the tangent line. So the slope of the graph of a linear function, let's look at example 1. Find the slope of the graph of f of x equals 2x minus 3 at the value of x equals 1. So here, if you guys notice, we know what c is, which is equal to 1. We can figure out what's f of c, or in this case, f of 1. So you plug it in, you get 2 times 1 minus 3, which would be negative 1. All right, so we're looking for the slope tangent at x equals 1. So the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. We substitute, we're going to get the limit as x approaches 1 of 2x minus 3 minus the negative 1 that I just found right there, divided by x minus 1. We simplify further, so the limit as x equals 1 of 2x minus 3, and then plus 1 over x minus 1. Simplify one more time, you're going to get the limit as x approaches 1 of 2x minus 2 over x minus 1. Now, again, if you try direct substitution, you'll notice you get an indeterminate form here, 0 over 0. So that means that we just have to factor the numerator, if you notice, has a common factor of 2. So the limit as x approaches 1 of 2 times x minus 1 over x minus 1. We eliminate that, and then we just have the limit of a constant, and in this case happens to be 2. So we can say that the slope, right, the slope tangent is equal to 2 at x equals 1. And if you guys remember, pretty much the slope of a straight line is a constant, which in this case happens to be 2. So that confirms our answer that for any point here, it's always going to be equal to 2. Now let's look at a little bit more of a nonlinear function, right? So find the slope of the tangent line to the graph of f of x equals x squared plus 1 at the value of x equals 1. So again, c equals 1, f of 1. If you substitute, you're going to get 1 squared plus 1. So that's 2. And then again, we're looking for the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. Substitute the things you have f of x, right? So the limit as x approaches 1 of x squared plus 1, and then minus 2 over x minus 1. Remember, that's f of 1, right? Looks like I think you do. So minus 1. All right. So right there, we have the limits. We simplify. We have the limit as x approaches 1 of x squared. Positive 1 minus 2 gives me negative 1 over x minus 1. And if you guys notice, we have pretty much a difference of squares on top. So the limit as x approaches 1 is going to be x plus 1 times x minus 1. The x minus 1's divide out, and we're left with the limit as x approaches 1 of x plus 1. And that's going to be equal to 1 plus 1, or 2. So if you guys were to look at a graph of this particular parabola, all right, something like this, we're pretty much at 1, so our slope seems to be 2. So it's going to be something like that right there. Now, the next part, the limit equation that we've been working with is so frequently used that a special notation is used. So we call that the prime notation. F prime of c is used to denote the slope of a tangent line to a function f of x at x equals c. Therefore, f prime at c is equal to the limit as x approaches c of f of x minus f of c over x minus c. So again, f prime of c is the slope of a tangent, of the tangent line, right? The slope of the tangent line at x equals c. And then we will call f prime of x f prime of x, the derivative of f of x. So f prime of x is what we call the derivative of f of x. Don't forget that, right? That's why I'm rewriting it right here so you guys see how important this vocab is. Okay, so let's look at example 3. If f is a function for which the limit as x approaches -2 of f of x minus f of -2 over x plus 2 is equal to 0, then which of the following statements must be true? So x equals -2 is a vertical asymptote of the graph. So do you think that's true or false? So just because now part A, if you guys look at it, x equals -2 is a vertical asymptote of the graph. So we can say this is false, right? This is false. Because that although the denominator contains x plus 2, the presence of the limit statement make this false, not pertinent to what is happening at x equals -2. All right, so they're telling us that this is pretty much like a derivative, right? So be careful there. For B, we can also say this is false, right? Because the function f of x, if x continues at x equals 2, it doesn't really matter what's happening at x equals 2 because we're not talking about x equals 2. We're talking about x equals -2. The derivative of f at x equals -2 exists, right? So this is true. The reason this is true is because the definition of the derivative value is 0. So it's true because pretty much if it has that equals 0, so that means that they're already telling us that it exists. So that's important to take right there. So f is not defined at x equals -2. F must be defined in order for the derivative to exist, right? So here, actually it is, f is defined if the derivative exists. And they already told us it does. And that concludes the notes for today.